Hello all, in this lesson we're going to be studying the early models of the atom. If you've had chemistry before, it's going to feel a lot like that at times. The homework associated with this lesson is really short and really easy, I promise. And our do now is just this little bit of reading and this one question down here at the bottom. So the first model that you guys are expected to know something about is Thomson's model of the atom. Thomson was an English chemist, and basically his idea was that if you had an atom, it would be a solid sphere, and it would have an even mix of pluses and minuses. And because they're so evenly mixed, and he would think of the electrons like little plums in a bowl of pudding, then he called this whole model the plum pudding model. And then we have Rutherford. Not only was he a supermodel, he was also an important English chemist, and his model deserves a lot of merit. He first had a criticism of Thomson's model when he considered that its even mix of positive and negative charges would make the atom so neutral that it would be unaffected by electric fields. Here's why. In Thomson's model, you had your atom like this with the pluses and minuses evenly distributed. So they would be able to sort of cancel out each other's Coulombic effects. So consider it basically like a neutral particle heading through this field. It wouldn't be pushed this way or pulled that way as a result of it being neutral. So Rutherford designed an experiment, which we'll go over on the next few slides, that basically put this idea to the test. Like, what would happen if you took a particle like an atom, whether it looks like this or not, and exposed it to Coulombic effects? So you exposed it to positive or negative charge. So he used a setup a lot like this, where he had a gold foil, and the gold foil is, of course, made of atoms itself that has protons and electrons, or the pluses and the minuses. And he thinks that they are all going to go straight through if the atom is neutral, and they won't be deflected in any way. And when they strike this fluorescent screen, it'll light up. So that's sort of what he thought would happen. They would all just go straight through. But the observed results were that a lot of them went straight through, but also many of them were deflected at angles other than going straight through. So this is basically the reason why that would happen. What you've got here is the nucleus of 3 gold atoms. The nucleus is positive, and what Rutherford is shooting at them are these alpha particles, which are a product of the decay of uranium. So alpha particles also have a positive charge, which you need to know. So when these positive charges interact with these positive charges, you'll see them change direction. So they all start out going in straight lines. And here's where you're going to see some of them start to change direction. Especially this one is going to have a full-on collision, and it looks like this one and maybe this one are going to come close enough to the nucleus to interact using Coulombic effects, positive versus positive. So let's watch what happens. So this one has done a collision, so it's going to rebound backwards. And now this one and this one are flying close enough to the nucleus to get their positive repulsion. So watch this one and this one. Did you see them change direction? So most of the bombarding particles pass through the foil, and the reason for that is that the foil was actually mostly empty space. And Rutherford's new model of the atom reflects that. We have this small nucleus in the middle with a lot of empty space around it. But additionally, a very small number of the bombarding particles were deflected. I counted 3 in the previous slide. And the reason why they were deflected was either they directly collided with the nucleus of an atom, or they flew close enough to the nucleus that they were able to be repelled using positive-positive repulsion or Coulombic repulsion. So let's label these parts. So the nucleus is here, and according to Rutherford's model, it is small, but also positively charged. And our electrons are going to be outside the nucleus in these sort of nondescript regions. Now, about these electrons, they're spinning around the nucleus like this, which means that they're changing direction at every moment. And with a change in direction, you also can consider that acceleration. So yeah, these electrons are accelerating. And in previous lessons, we've learned that when charges are accelerated, they produce electromagnetic radiation. And also that, that production of the electromagnetic radiation should sort of sap the electron of energy over time, because it would be losing energy through the waves that it's producing. So basically, Rutherford was thinking that it's possible that as these guys spin around the nucleus, they're losing energy, and they're going to be spinning closer and closer and closer and closer and closer to the nucleus until they collided and collapsed into the nucleus. But he noticed that didn't happen. So he knew there was something else to this, but he was able to predict that if the electrons were just particles moving around the nucleus, then they would eventually collapse in. This is where Bohr comes in. Bohr was able to show that the electrons would never collapse into the nucleus because their orbits belong to quanta, which we talked about in our last lesson. So he said all forms of energy are quantized. That is, an electron could gain or lose kinetic energy only in fixed amounts. Or in other words, they couldn't gradually spiral into the nucleus. Bohr really only studied the hydrogen atom, however, and the reason for that is really easy. It's because the hydrogen atom has only one electron, so it can only occupy certain specific orbits and no others. And the electron in the hydrogen atom can jump from one orbit to another, but it has to absorb a certain quantum of energy. So all of these allowed orbits, which is what we're calling them, like the orbits that make sense, are based on certain quanta of energy, which could be represented in electron volts or joules. So let's take a look at a diagram. This diagram shows you what the orbits are. So this is for a hydrogen atom, but you have orbit 1, 2, 3, 4, 5, and 6. Things that you need to know are that the lowest orbit is the best orbit, but you can move to a higher orbit if you absorb energy. So that's what these arrows are saying, that as the atom absorbs energy, electrons can go up to higher orbits, but they can also go from, let's say, this orbit, which is number 4, it can go from 4 all the way down to 1, but it would have to release energy in the process. So moving up orbits absorbs energy, and moving down orbits releases energy. So these are called orbits or energy levels. And I also have a ground state versus excited state idea. Ground state is going to be the lowest available orbit, and excited state is when you're above the lowest available orbit. So here are my questions. Can electrons gain energy in any amount? The answer is no, it may only absorb energy in specific quanta. In this diagram, the orbit that has the most energy is number 6 because you would have to absorb the most energy to get there. The ground state for hydrogen is going to be n equals 1 because that's the lowest available orbit. And one excited state for hydrogen could be n equals 2, 3, 4, 5, or 6. So in the previous slide, I was saying that atoms can lose, or they can gain enough energy that electrons can move up to higher energy levels. I wanted to point out something on this slide, which is that if an electron absorbed more energy than its highest available orbit, then it would just have to leave the atom altogether. And this is a real process. It happens all the time. It's called ionization. Ionization is when an electron leaves the atom, and the product of that is that you have created an ion. So ionization creates ions, and it's always just because you've lost an electron because it gained so much energy that it left. So these two diagrams are on your reference table. You may have seen them before and you should find them now. But what they do is they show us the available energy states for two different elements. Hydrogen, which is what Bohr studied, but also mercury, which is an interesting choice, but I don't know why they chose it, but it's on there. The ground state is labeled as the bottom level. For hydrogen, it's N1, but for mercury, they use letters A through J. And for hydrogen, it's N1 through N6. N equals infinity is the ionization level, which you can also see as level J for mercury. So over on the right-hand side, we have our energy of each orbit, and it's listed in electron volts. And it also goes from the most negative value up to 0. And the reason for that is because once the electron reaches the ionization level or the infinity level, then that means it has no energy left at all, because the energy would only be there if it were in an orbit. So we order those energies almost backwards in a way. You have 0 at the highest orbit, and then negative 0.38 at the highest available orbit for hydrogen, all the way down to negative 13.6 for the lowest available orbit. So technically this is the highest amount of energy when you're looking at a negative side of a number line, but 0 is the max. So the cloud model is also something that you guys should know about. Basically, the cloud model says that electrons are not actually in specific orbits like the previous diagram suggested, but that they're actually only in these regions of high probability of finding an electron. So in this question it says, why do you think Bohr's model could explain the electron orbits for hydrogen but no other element? It's because hydrogen only has one electron, but other elements have more than one electron, which makes their electron clouds more complicated. All right, so let's talk about atomic spectra. Spectra is referring to sort of like the light spectrum, especially the colors. And you can see those here. And this is the spectrum for helium and the spectrum for hydrogen, but what are these spectra? So basically, you may remember that electrons can absorb energy to move up a level, and then they can release energy and move down. And when they release energy and move down a level, they emit light of specific colors. So if you go from let's say a super high level, you're going to release a lot of energy, and that's going to correspond to a violet or a blue. But if you fall from a lower level, you'll release less energy, and that would correspond to, let's say, a red. The more electrons the atom has, like helium has 2 electrons for hydrogen's 1, the more electrons it has, the more bands you'll see. So again, these red are representing relatively small drops in energy from lower levels to the ground state, and the bluer, more violet bands are representing larger changes in energy from higher energy levels to the ground state. We can do calculations about these sort of spectral emissions using this equation, which tells us that the energy of a photon is equal to its initial energy level minus its final energy level. So you can find that on your reference tables. EI is the initial energy, EF is the final energy, and you just need to subtract the two. So let's try this question as an example. A hydrogen atom emits a 2.55 electron volt photon. As it moves between energy levels, and again, this was the hydrogen atom. So let's find 2 energy levels that are 2.55 electron volts apart. So let's see. If we have a ground state at negative 13.6, and then n equals 2 is negative 3.4, this difference between these two numbers is larger than 2.55, so it's not going to be this change. But this one is tempting, so let's give it a shot. You can actually sort of ignore these negatives and just treat them as positives for now. So let's see if we can get 3.4 minus 1.51 and see if we can get 2.55. So I was only able to get 1.89. So I'm having another idea. What if we do 3.4 minus 0.85? So my suspicion was correct. This one comes out to be 2.55 electron volts. So what that really means is that in order to release a 2.55 electron volt photon, the electron must be moving between this energy level and this one. So it must be moving from, sort of hard to read, but it looks like it's coming from N3. I'll try that again. It looks like it's coming from N4 to N2. And there you have it. In order to release a 2.55 electron volt photon, the electron must move from N4 to N2. So these bright line spectra can produce many different colored bands. And the reason for all those different colored bands is because of all the different options for how you can start somewhere and get somewhere else. Like imagine that you were starting at N6 and going to N1. There are 1, 2, 3, 4, 5 ways to do that. You can go straight from 6 to 1, releasing a ton of energy all at once. Or you could go from 6 to 5 and then go all the way down. Or you could go from 6 to 4 and then go all the way down. Or from 6 to 5 to 4. So there are so many different ways to do that. But I do want to do this question together because it's going to help you on one of your bookwork questions a lot. So this question says that basically if you're in any excited state for a hydrogen atom, and that excited states would be 2, 3, 4, 5, and 6. If you're in any excited state, no matter what, if you go from an excited state down to a ground state, that you're going to be releasing the same color of photon. So let's check it out. So as you go from N2 to N1, the difference in energy is 13.6 minus 3.4, which is 10.20 electron volts. So ultimately, I want to convert this into a frequency so that I can get a color of light. So I'm going to need the electromagnetic spectrum, but I also need to convert this electron volts into joules first. So I'm going to do a conversion factor, and I'm going to multiply it by something that has electron volts on the bottom and joules on the top. So I just checked my reference table, and I found that 1 electron volt is equal in size to 1.60 by 10 to the negative 19 joules. So I'm just going to multiply these two numbers, the 10.2 and the 1.6. And I got 1.63 by 10 to the negative 18 joules. Now I'm going to come down here and we're going to use the equation from our last lesson that says E equals HF. And I'm going to rearrange this for frequencies. That's going to be E over H, which is of course Planck's constant. The E is 1.63 by 10 to the negative 18 joules. And Planck's constant is 6.63 by 10 to the negative 34 joule seconds. So once you go through this calculation, you're going to find that the frequency of light produced is 2.46 by 10 to the 15 hertz. And in basically the last step of this question, we need to find this frequency on the electromagnetic spectrum. 2.46 by 10 to the 15 hertz is going to be in this area somewhere, which is in the ultraviolet region of the spectrum. So, all told, you will always get a band in the ultraviolet spectrum for a hydrogen emission. And, you know, I probably could have just read this question a little bit closer and seen that you always get an ultraviolet emission when you go from 2 to 1. But the reason why I really did all the math and everything was because on the exam you won't get this particular diagram, but you may be asked to do this particular question. So you need to go through the steps of converting and make in the equations to get ultraviolet. All right, so absorption spectra are just like emission spectra, except they're the opposite. So an emission spectrum looks like this, where you have these bright colored lines representing the energies that electrons emit as they return to ground state. And below that, we have the absorption spectra, which is the amount of energy. These are these black lines here. This is the amount of energy absorbed by electrons as they go into their excited state. And yeah, they're basically just opposites. So if you had an absorption spectrum and an emission spectrum for the same element, you would see really the same bands. They would either be colored or they would be black. Black is absorption and colored is emission. Let's answer these questions. How are emission and absorption lines related? Well, they are the same, they're just reverse of each other. Emission lines are produced this way, and absorption lines are produced this way. And with that, we've reached our pair up. So expect me to make copies of these questions for you. And the summary, though, I need you to copy down this table on your own paper. We'll answer the particular questions in class. Thank you for watching.